Yep, hi everyone, welcome back. I guess after all those exercises that we have done, I think we are now fit into moving into chapter 5. Chapter 5 is going to dwell with electrical propulsion. Now, remember this, we have all completed all those necessary chapters to see fuel based I would say rocket engines, and then which is solid or even liquid. Now we will actually see how we can proceed with another type of propulsion system. Now, for this particular propulsion system that we are here to discuss, especially in chapter 5, electrical propulsion system, we want to basically know why is that we need to design another system. As it is, we have already have a system which is working, the solid propellant or even the liquid propellant. Why is that we need to now look into this other options? We'll justify that, and I'm very sure at the end of this particular lecture we will see how both of these particular engines come into play, both these technologies come into play, and how they complement each other. Okay, so go on. Now, if you look at the comparison between chemical and electrical engine, chemical engine again is what we have already learned. We have liquid, we have solid, and we have been discussing that quite a bit. And let's see now, fuel. If you look at the fuel with the usable energy, this goes into that chemical engine, and you get basically the force or the thrust, m dot ce, yeah? Effective exit velocity. But on the other hand, if you look at electrical engine, fuel basically goes in, but you have something else, electrical device, which comes into the play. So that is a fundamental difference. That is a fundamental difference. Okay, in solid fuel you don't have that. So that is a fundamental difference between our chemical and solid electrical engine. For example, you don't, now sometimes you need ignition. Yes, it's true, you need ignition, but you don't need ignition throughout basically to operate the chemical engine. That's for sure, you don't need that. Okay, in electrical engine, you not only you need ignition, but you need to keep on igniting the electrical system in order basically to give you the amount of force that you want or the thrust that you want. That is the difference. It is just, imagine this, if you are playing let's say firecrackers, you do ignite, right? You ignite, then done, and it works. That is chemical engine. But in electrical engine, you need to actually keep on igniting it. That means if you have a matchbox, I think you must end up actually keep on actually igniting it, so that it keep on working. So that is a fundamental difference for you to understand the very, very basic what is the difference. Then we will see how these actual differences will be beneficial to us. And if you look at the characters, basically fuel and energy source is always separate. Okay, yes, how you want to imagine this? For example, solid boosters, all of them are together, right? So in electrical engines, they are separated. Fuel is electrically burned. As I've told you, we have to keep on actually pumping electricity in order for us to burn the fuel. If you stop electricity, that means we are done. So which means that if I were to ask you what is the prime importance, what is the crucial requirement for electrical engine, it's in the name itself. You need electricity. Now the biggest problem we already can deduce now. If you're already in a space business, you already now can imagine, oh my god, you need electrical system. Now power system or power or electricity in space is so scarce. Yeah, and it is not easy basically for us to harvest energy. And we need to keep on pumping electricity for the system. Can we afford it? So let us see throughout this lecture what kind of energy that they need, or rather what kind of electricity, what is the amount of electricity it is needed, what kind of voltage is needed, what kind of current is actually needed, can we afford this, or for which kind of applications is okay and which is not. Mass flow is smaller than the chemical engine. Well, yes, the mass flow is smaller. When the mass flow is smaller, which means that the force is smaller. That is another thing that we need to think now. Remember our liquid engine, even solid engines, I would say our chemical rockets. Our chemical rockets, especially the solid boosters, are being used to give us so much of thrust or force so that we can get out of earth pool or gravitational pull as soon as possible. The faster the better. That is the reason for us to even to put the boosters, or rather to include the boosters in the system. So we have understood that. So now here we are saying that the mass flow is smaller, which means that my force is going to be also smaller. You got to think now. Well, that means we have a very, very well selective application, so to say. So let us see what else. Effective exit velocity is high. Wow, that's good news. Effective exit velocity is very high. That's very good. So now, for higher than chemical engines. Now you're going to be very, very careful here. If you see the mass flow is small, but the CE is big. Therefore, you may have a less force. But although CE is big, but we have understood something. CE, when you want to design an engine, we have actually discussed about all these equations that we have invoked in our exercises. Throughout the equations, you have seen that, look, for liquid engine rockets and the solid engine rockets, we have made sure that WE is huge. That's all what we did, right? And again, what we have started doing it, we are actually start looking into the system to provide us the best force or the best thrust for us to basically to propel. That's how we have started designing it, right? There is no way, and we have only provided the WE based on that particular force. What happens after that? That means what happens to delta V? That is, we can't control, because why? That also depends on the exact CE now. So which means here, according to the rocket equation, when the CE is, or effective exit velocity is very high, or very, very high, it is very, very good for delta V. That is very positive. But unfortunately, for the engine itself, if the force, the mass flow is low, the force is going to be low, which means that it cannot help me to push away the engine or payloads out of planet Earth fast. So you see that there is advantage and there is disadvantage. But we must actually also correctly say or correctly deduce for which applications that we want to use electric propulsion. Thrust level lower with respect to the start mass. Obviously, I've already explained this. So, which means that I cannot use, so if you ask me before we start going further, can we use electrical system to for rockets to start? I don't think so. It is not as good as boosters. It's not as good as my chemical engines, my liquid engines. I can't, because I need actually a very high amount of thrust level. I need a very, very high here. Delta, my flow must be high. More fuel go in, more thrust I have. So it's important. But don't forget, when more fuel go in, higher thrust you have, it doesn't mean your engine is efficient. your ISP will be low. You will see afterwards. You will see afterwards for all the ISPs that we have seen, specific impulse that we have seen for our chemical rockets compared to what we have here. Okay? Go on. Alright. If you look at the simple comparison for electrical engines. Now, I've also explained this. If you look at all those delta V's that you have. Now, if you look at Geo, Leo, you see planet orbiters or even comet rendezvous. Okay, let me dissect this clearly. Up to this level is all electric. Well, I would say safely you can say it is a Earth-oriented mission up to this level. You don't need more than like 20 delta V. You don't need. In fact, all the rockets basically are hovering around here. Okay, all your rockets basically hovering around here. Okay, so which means that for Earth-oriented missions, yes, you have chemical 1 stage, 2 and 3 is good enough. It's done. Delta V is good enough basically to take us out of the planet Earth. But unfortunately, they are not good enough when they want to actually come to here because they die. You see, this is the maximum they could actually give you. Which means that if I want to do a comet rendezvous, I cannot be using a propulsion system which is based on chemical system. It simply doesn't make sense. Or you can do it, you can force it to do, but then it will be huge amount of tanks you must have. It will be something that we haven't designed before. So it doesn't make sense to do that. So according to basically the rocket equation, based on the payload ratio is why you want payload ratio high? You want a payload ratio high or low? Higher payload ratio is good, right? Lower payload ratio is bad because start mass and okay, start mass. If your payload ratio is 1, that means your 1 kilogram of let's say a satellite that you want to bring up, you need 1 kilogram of basically rocket, which is doesn't make sense. Okay, so you need to understand that what is needed and when to use these particular solutions. So it means that looking like the requirement, maybe I can consider electrical propulsion for an interplanetary mission rather than Earth-oriented mission. Geo mission, geostationary orbit, planet Earth, Leo, low Earth orbit, planet Earth, orbiter. Basically, if you talk about maybe a moon mission, you can actually look at orbiters. All these are basically within, you can say that within our Earth vicinity. So for this kind of missions, it seems that I think I would go for chemical engines rather than electrical engines. But if I want to go far, looks like I have no choice. I need electric engines. That is the reason that actually we are looking into electrical engine in this particular lecture in chapter 5, because it's also very important. Now, if you look at effective exit velocity, CE, with respect to the payload. Okay. Now, obviously, when payload ratio is just higher, obviously your your effective exit velocity basically is going to actually peak and just come down. Now, what you have here is basically an average of peak for all those cases of delta V. Now, if you want a very high delta V, that means what? That means you are very heavy, you know. You are very heavy. That means that payload ratio is not going to, that means you are carrying a very less amount of payload. Then you are here. But the delta V is very, very high, you know. You need. But payload, it goes very, very low. But assume that you want to, your delta V, you go on small, you don't need so much of delta V. Your payload ratio will be quite high. Means that what? If you want to fly very far, you can't send big things. If you want to fly very, very short distance, with the current technology, you can send a very big thing. Okay? You want to send, let's say, with this technology, you want to send huge payload. You can reach only up to a certain level. Maybe up to here. So it reduces it accordingly. But one thing good that actually in this graph, what it says that effective exit velocity. For all the peak which has been optimized, you look at the CE, more often than not it's about 50. See? It's about 50 effective exit velocity. So you can see this is a very, very good, extremely good graph, because that tells you no matter what engine, most of the engines that you have, okay, your optimum will be about 50 effectively. That's the maximum that you can go in, 50. If you start actually doing more, no, because the peak is 150. So if you already can reach about 50, you are already excellent. So that's a very, very good indication. Yeah, 50 effective exit velocity. Okay, CE. Okay, this is a kilometer per second. All right, this is about that. But this is also calibrated based on the payload ratio. Okay, based on the payload ratio. This is calibrated. All right, go on. All right, now for electrical engine. So electrical engine, I have divided into three, basically electro-thermal engine, I will explain, MPD, plasma dynamic engines. When you say plasma, you already know it's already a very ionized stage, plasma, electrostatic engines. So three types of engines that you have in electrical propulsion system. Now, if you look at this, I want you to focus resistor jack, arc engine, very good. Here you have a field accelerator, one example that we have, it's quite typical. And the final one, electrostatic engine, look at ionic engine. These are the important ones. Again, I repeat, important resistor jack, arc jack. For MPDs, field accelerator. For electrostatic engine, ionic engine. Okay, let's see the operation. If you look at all, it's stationary, but some of it, I say the pulse. What do you mean a pulse? Pulse means got plasma. That means what? The engine works based on ionization. That means even if you put a fuel into it, the fuel must be ionized. That means it will be in a plasma state. Okay? So when it's ionized, it's free ions are there. If you look at our engines, chemical engines, they are basically all stationary. That means the fuel don't change any form. You give liquid fuel, they are still liquid, then they burn. When you give solid fuel, they are still solid, then they burn. They don't change any states. But here, they come into gas form, they may be ionized. So when that happens, you have a pulse. That means plasma states is needed. So there are two designs sometimes. Okay? Resistor, there is only one design. Arc jack, it can be stationary, that means there is no change, but it could be also a plasma state. MPD, automatically plasma. Ionic engine, stationary. Can be stationary, okay? Usually stationary or plasma field. I think I've given you the plasma type here for ionic engine also. Okay, now look at the fuel type. Now fuel type, possibly light. Good news. That means it is not heavy. Possibly light, then what? All form of gas. Okay? For example, what kind of gas? Afterwards, I think show. Typical gas available: hydrogen. You have ammonia, N2H3. Sometimes need all form. For example, arc jack. Arc jack also can use hydrazine. You can write that. One exception to arc jack, they can use basically hydrazine also, N2H4. Okay. Then what about MPDs? Magnetoplasma dynamic engines, possibly light, because all gas they use. See, whenever you start actually using gas, then it is lighter. It is better to use gas because it's light than to use a fuel or even solid. Obviously it's lighter. So you can already now imagine that means the electrical propulsion system might be lighter compared to chemical propulsion system, which is true. It means it's good news for us. Alright. Electrostatic engines, possibly heavy. We will see why this becomes heavy. Although you have a gas as a fuel. But typically you do have actually the lighter ones also, but possibly heavy. I'll tell you maybe here itself, possibly heavy just because of what? Because if you need so much of, let's say, electrical energy. When you need so much of electrical energy, then the engine becomes bigger. Engine's requirements become bigger. That means you must have actually power supply, which is huge to support the engine. Now look at this ionization grade. So these are ionization grades are what is actually is given here. If you look at it, 0, that means I told you resistor jack stationary means it is as good as the fuel doesn't change the state. You give gas, it will remain gas, it won't ionize, you won't have a plasma state. Okay, the rest you may have a mixed state, but you do have a plasma, you will have an ionization. Okay, go on. Alright, now this is very, very important. This is where what we are going to learn, the difference, the fundamental difference between electrical engine and chemical engine. Specific impulse. Look at that. Look at this. Can you imagine 2000? Now I take this example. 800. Well, I would say that typical. Yeah, we have our SpaceX recently, right? Launched capsule, Dragon capsule. They're going to come, I think, they'll return. But those two astronauts have flown a space shuttle, right? So they have their comments on the flight. If you look at it, they said that look, it is a bit rough because they have flown space shuttle. Space shuttle is actually a beautiful, well, man-made spacecraft, I would say. Just like the Russians has Buran, it was so beautiful. But unfortunately, they are not so super efficient. If you look at the actual specific impulse we have done in our lecture, SSME space shuttle main engine, that's about 455 seconds specific impulse. That is for space shuttle. And you look at my specific impulse here. Look at my specific impulse down here. 455 for space shuttle with all those actually safeties that we have for liquid engines. But look at my electrical engines now. Now, if I have a very high specific impulse, what it means, I should be having a very good delta V, period. Although my force is low, it only gives me only one problem. While launching, I cannot get out of planet Earth fast, period. Kamikaze. The more I stay, the more I'm going to lose fuel. Okay. Look at the thrust. I told you this one, just like, look at that. This is pathetic. This is totally pathetic for any rocket engine. You can't even put a bicycle on top of this, basically to launch. Resistor jack. Can't. Yeah? So, leave alone human. Leave alone satellites. Okay? You can't. You can't even put a racing bike there. Please launch. No. Because this is so little. So looks like to escape planet Earth while launching, this is not a good solution for rockets. But it is a very, very good solution for interplanetary missions because of good delta V. So we can use it. Efficiency. Well, in a way, not too bad. Okay? But look at this fellow. Up to 90% of efficiency, you can't even imagine with any rocket, the chemical rockets. You don't have this. Okay? Now you know why it is so efficient. Because there is so small amount of fuel that you put in and so much of delta V that you can get. So the engine is so efficient. Remember the specific impulse. Specific impulse tells you what? Specific impulse tells you the efficiency of the rocket engine. So higher specific impulse, higher efficiency. That means for a very small engine, I put a little fuel, it gives me a so efficient, very small thrust, but so efficient delta V because of its CE. Because of the CE. CE is so high compared to my force. So it is efficient. Go on. Alright, let's start with the electro engine types. Resistor jet is the first one. It's the most typical one. Not a very, I would say, popular. It is, I would say, entry level for electrical engine. Advantages: simple design, obviously, high reliability, high thrust density, reaction capabilities, efficiency up to 80. Just now we have said that is actually a working efficiency. Yeah? This we can push this efficiency up to 80%. There are optimization process, etc. But the typical one not up to 80%. Large selection of fuel, of course, it is very flexible. Remember, resistor jet. Well, fuel you can have actually even a hydrogen, you can have ammonia, etc. So that's fine. Then I will explain this. You have a coil parallel. A is basically a coil parallel to flow A. Now what is this? Okay, this type of engine is simple. Remember this. You are now pumping fuel which can burn if there is a heat. What you are doing is you are heating up, let's say, a filament, a coil, to become very hot, and you splash the fuel on top of the coil. What will happen? You'll burn. That is the fundamental. That's how electrical propulsion system works for resistor jet. This is actually stationary. That means that there is no plasma, there is no ionization. So it's very simple. But there is no contact. There is no contact. Electricity runs as usual and heating up. Okay? And it's heated up. You splash the fuel on top of it, it burns. So now this coil, what they have done here, they can put the coil like different kind of design. Coil is parallel to the flow. You can do that. You can try this. Normal to the flow. Wolfram sphere, which is this. See, wolfram is basically, tungsten and wolfram is used for pulp. You can also use that. Okay? You put this basically sphere. Then when they are already hot, you splash the fuel inside. What will burn? It burn. Once burned, basically it's going to give me a thrust. That's the fundamental. Current is focused on the wall here, for example. So it's all the same thing, but they have varied the design. The whole thing will be hot. You splash the fuel. That means you can have the fuel spread at the wall. So contact area bigger is more efficient. So that's how they have here. For example, wall is heated. Wall is heated. Current is focused to the wall. Here, there is like a tapper going into, focusing to the wall. No problem, because you want to focus the fuel. A very small amount of fuel. What you found here, let's say you put in a very small amount of fuel. Fuel gets splashed everywhere. The burning maybe is not efficient. So what you do, you start focusing the fuel at some wall, a particular wall. That's what happens here. So there is so many types, but the fundamental is very simple. On the electricity, coil is very, very highly heated up, splash the fuel on top of it, and it's burned. Bingo. Almost like a car, so to say. But car is actually has a different actually system because we have a burning, fuel burning, different. Okay. Now, effective exit velocity is the inverse. Now, you want to calculate the effective exit velocity is basically the inverse of mean molecular mass. Obviously, I told you, remember, the effective exit velocity is very, very much governed by the actual mass mole, mean mass mole. Why? Because of the fuel. You are splashing the fuel is going to give you a good or bad. That's it. You have a very, very big mass. What is going to happen? Value is going to be dropped, right? Value is going to drop. So you must have very, very small amount of mass. Means that the particles are very, very small. so that the burning is going to be complete. So that's how it is. Okay, this is the first type. Gone. A disadvantage would be lower specific impulse, of course, fine, but don't forget, lower specific impulse compared to other electrical propulsion system, not compared to the chemical propulsion system. Okay, go on. All right. So these are the typical one resistor jets that you have. All this is available, huh? All this is available. So I've shown you the fuel, typically hydrogen. Okay. You have this is ammonia, NH3, ammonia. Configuration of the heaters, these are all typical one. Look at the thrust. Still not high enough. Still not high enough. Okay. Specific impulse, but quite encouraging, right? Quite encouraging. Specific impulse. Quite encouraging. 800 plus. It's already fantastic. Remember, Space Shuttle has 455. It's already good. Thrust efficiency. Hey, excellent. Not bad. Good. Chamber pressure. Reasonable. Go on. Okay. Now, arc jet. There's now resistor jet. This is basically its arc jet. Now, if you look at arc jet, very importantly, you must understand this this particular system of electrical propulsion is going to work on ions, which means that it is not static. That means you pour fuel, the fuel inside must be ionized first. Then you have free ions, and the free ions need to, now when you have a free ions, there is no heat inside. What will happen? It will be still like floating. So in order basically to have this ion projected outside, so what exactly that you do? You heat it up, ionize, and then it is going to be just pushed out. How to do this? Now what we have done here is different. This is just the fundamental that you need to understand. In arc jet, you have current. You have current. Now, just now, the current is flowing just to heat up the particular coils. That's it. Nothing it does. Now, you will have a current system which is flowing through the chamber. You will see afterwards. It will be flowing through the chamber. When current flows through the chamber, it creates magnetic field. Right or wrong? Right hand rule. Let's say current is here. Let's say my source of current here. Let's say anode. Anode is here, positive, negative. Positive current flows. Current flowing. This one, I think you guys learn when? Standard 5 or maybe kindergarten? Huh? Probably, yeah, standard 5, I think. Standard 5 or Form 5 or Standard 5, I'm not sure. But it's still, so thank God to our teachers. They taught us something that I can still use up to today to teach you guys. It's very good. So, you have current. Then, when the current flows, assume that there is one, let's say anode and cathode. Current flows, you will have magnetic field. Right? So assume that magnetic field is towards here. Magnetic field will be circle. I can pick whichever I want, I'm just giving you one example. Magnetic field can be circle. Current goes up. This is B field. So I pick one of the field, B field here, maybe tangent to this. I pick one. I just want to give you an example how this happens. So my current, my field, I pick that one, and I have a resultant force. So the flow, whatever the free ions here, will be rushed into out here, and that flows that creates the jet. That creates the jet, and that respects our rocket equation. That's how it is done. So you keep on pumping your current, keep on pumping your fuel. The fuel will be at all ionized form. Why is ionized? How it becomes ionized? Is it ionized because of the electricity? No. It is ionized because you need to preheat it. How you want to preheat it? You can use Wolfram, for example. Heat the fuel, very, very high heat, and then splash it inside. It's already ionized. When it very, very high heat, it's already ionized. Okay? When preheat, that ionization takes place, it's already ionized. It's all free. But they are not directed anywhere because there is no force, because we are not burning them. So what exactly happens? Something must direct them. So there should be one force. So this invisible force of what? This is called, what force is this? Lorentz force. You have this law, there is two laws is important here. I think you have studied Laplace force and Lorentz force. Both of them are interrelated. So Lorentz force, when you have a magnetic field, when you have electrical field, and you have a resultant force. And the invisible resultant force, because magnetic field also is invisible, electric flow is also invisible, the force is also invisible, the electron also is invisible. The only thing that you can see is that jet coming out here, that's all. But what happens inside is all invisible. I hope our theories are all right, that mankind's theory is right, because somebody comes up with a different theory, but as far as up to today, that invisible theories complies to our math. So we have proven that, so that jet is due to that. Okay, that's the difference. Go on. So if you look at the equations, more importantly, you look at it, ideal gas, again, this is standard continuity. I think all of you are familiar with that. Energy equation. Now, important here, I've just introduced that Laplace. This is actually a Laplace equation, you know. This is a Laplace equation. J cross B, J is current density, specific current density. That means current with respect to the surface. Cross B. Be careful, this is a vector cross product. Okay? Now, so technically speaking, the balance, we can write balance of energy, the conductance. In this case, basically, we need to invoke also the conductance. Conductance basically sigma, the distance, how long is that passage, the area, and the resistance. This is electrical resistance, it's an ohmic resistance, ohm. This has to be given. Why? Because when you design an engine, we will know what is the resistance inside. That we should be able to give. So when you substitute everything inside, we should be having a particular equation which can help us to solve the W actually, the exit velocity. Don't have to worry about this. This is quite straightforward. So this it can be deduced also through experiment. Okay, watch this. Still our chapter 3 equations are valid also here. Again, it's an adiabatic condition, just like our chemical rockets here. Go on. Okay, now look at here. This is how it works. I think I've explained a bit just now. Arc engine setup. Now assume this. Assume this is basically positive, negative. Okay. Fuel flow. Before fuel flow comes in here, fuel flow will be injected inside here, and then you will have heating elements like this. These are heating elements. This kind of object, this we call it object. Now it is made of wolfram typically, just to heat up, so that it will be in an ionized state. Okay. So heat, ionization takes place. If you heat it too much, when it starts burning here, it becomes what? It becomes resistor jet, like just now. So you must be careful. Principle is more like similar, but look at the actual innovation. You heat it at the right temperature for it to get just ionized. Ionized, that means the ionization is already taking place here. What exactly happens here? There will be a current, invisible current, flowing from positive to negative, right? Yes? Positive to negative. When there is an invisible current flowing positive to negative, there should be also an invisible magnetic field B, just like I've explained. Okay, so you will have a force. Now again, go back to the equation just now. Remember this, J cross B, this is a Laplace law. If I substitute J, I, that means current, cross B with the distance, it will be Lorentz force. Okay, that is the difference. It will be a Lorentz force. Okay, and this basically will be also I. Yeah, this, the difference is just this. Whether it is basically is a current density. When you use a current density, then it will become a Laplace force. Okay, Laplace and based on Laplace law. When you use just the current, then it will be a Lorentz force. Okay, go on. So therefore, you create a flow, and when you keep on pumping the fuel, ionize, choke, ionize, choke. That's how RJ works. Okay, go on. Now, magnetoplasma dynamics, same principle. The difference is only one thing. In arc jet, the amount of ionization is lesser. Can you again, this much of fuel only heated up. This is already up to N. Why not? I make sure I give more options for the fuel to ionize, so that more fuel, ionized fuel, free ions, can get interacted or can be under the field of electric, and can be under the field of magnet, so that there will be a Lorentz force pushing, which is the actual thrust. Why not? So that is exactly the design comes here. Go on. This is what exactly happens. Look at the amount of, again same, pumping. But ignite that, not don't ignite. Ionize means what? Heat up until they are in a plasma state. That means what? They are already in ionization. That means they are free ions. Very, very important. If you don't have the B field, if you don't have the, see J cross B, say, if you don't have the B field, all the ions will be actually what? Will be here to anode. You understand? Will be attracted to the walls. They'll be stuck here. They won't flow because there is no force to flow. They will just keep stuck here. But since basically there is a electric flow, anode, cathode, there is electric flow. Because of the electric flow, there is a B field, that means magnetic field. Because of these two fields, there is a force. All these ions will be pushed out here, and you create a force. Okay? Now, understand this, not all of them are parallel to the actual thrust. So that is the reason here I have only shown that the one that effective, which is going to push that propulsion system parallel, which is the Z component. See, which component? X, Y, Z. This component. My Z. So here would be a matrix which is 0, 0, 1. Okay? Matrix vector X, Y, Z. So this component is, I'm just taking a Z component here. So X, F, Y, F, Z. This one will be, so F, Z, there is a component. But there is still a component F, X, F, Y, but it is not effective. It is not helping you to push. Remember our assumption of a rocket equation? The thrust must be parallel to the what? The thrust must be parallel to the actual rocket direction. So this is effective. Alright, now here, this is a very typical equation that you have. The actual force, pressure, throat, coefficient. Now this is important here. Now this is actually clear. This is in the chamber. Now this is due to the actual magnetic influence. So if you look at mu is basically magnetic field constant. Magnetic field constant. It is if you look at every magnet would have this. If you measure that, it is typically the unit would be Newton per ampere square. Okay, remember this. Newton per ampere square. So therefore you will have a force here. Okay, Newton per ampere square, and this will cancel off because this is I is your electric. I is your current. I is current. This is actually a magnetic field constant. Now please do write here. This is the diameter or the radial diameter basically for the anode. That means this the area, and this one is for cathode. Okay, this is a cross section. Cross section, total cross section. Don't get, this is not a radius, but it's a cross section. Okay, because I've already used A in a different. I don't want you to get confused again. But please do right here. This is basically a cross section of that anode. That means this whole thing. When you see here, if it's a round, just like a divergence, then you should have that anode is, and then you go inside, the cathode will be actually smaller. Okay, so it's a cross section, circular cross section if you write cathode anode. Okay, gone. Now if you look at, before this go, look at this design. I told you, problem is that I have only used one component, right? What about the X component and Y component? It is also happening, but it is not helping, right? What if I put a filter here, like a guide? I have a guide here. Then I can direct the flow to only Z component. Don't you think it will be helpful? Yes, it will be, because I won't have any wastage. Flow going here, flow going here, flow going here. Every flow I try to direct them, go this way, so that all this is going to propel my propulsion system or even my rocket. That's what I'm going to do. So I want to do this in different design. Go electrostatic, ionic. So this is ionic propulsion. Difference, same principle. Difference is acceleration guide. So in this acceleration guide, all these ions, free ions, I try to reduce it. Of course, there will be still some guys hitting the wall because you are subjected to that actual electrical field and magnetic field, no doubt. But the one that actually I'm pushing out, I know for the fact they are not going to go this way or this way. Everybody is going to respect the acceleration guide to go on a Z direction, so that I can propel in the flight direction. That's how this whole system is. So this is a fundamental still same. Okay, gone. Bit of equation. Now most important of this is this energy equation. I think you know. Now in this ionic propulsion, if you look at it, you have of course voltage, charge. Now this charge is actually ampere times by second. That means ampere times by the time, how long you are injecting electricity. So ampere second, voltage, everyone knows, volt, velocity, exit velocity, this is the mass flow inside. Okay, so effective exit velocity will be in this equation. Alright, now if you look at it again, my CE will be still lesser. Here what I'm doing is that I'm trying to estimate my WE, but my CE will be still lesser. I'm still respecting a rocket equation. My thrust will be basically the actual fuel, and with respect to the exit velocity, once exit velocity is come. It's quite easy, this is, okay, not very difficult. Fuel flow can be also estimated. So if you substitute, all the force can be calculated. If the I is given, you must know how much is the I. When the charge is given, I also should be able to be calculated, okay? Therefore, with respect to the voltage. Now, importantly, maximum ionic current have to be can be calculated here. Why is important? Maximum current here is important, because then you know how much actually you need to, how much of voltage you need to give out, or rather how much of voltage you need to provide. That is extremely important. Attention need to be paid here. This is basically the permeability of the proton flow, the ion flow. That means if you have electricity in the vacuum, how much they can flow. So if you look at the actual unit, will be Coulomb square per Newton meter square. Yes, okay. Coulomb square per Newton meter square. That should give you the permeability of that ion. Okay. Then you have diameter. This is a D would be basically go on the figure. Would be the jet. This will be the diameter of the jet. Okay. Basically, will be a diameter of the jet. So this will be giving you the total component of that ionic current. Go on. I think more or less we're done. Go on. Yeah. Okay. Now there's something that actually I need to discuss. Now maybe the last slide, please. You put in the. We will do exercise. Now, if you start calculating the current that you need. Now, this is a very tricky thing. That you will learn this in your exercise. When you look at the current that you need, we can't keep on pumping the current. Current is not a free fall. Current has a limit that we are okay. We set maybe about 3 amperes, or maximum, let's say 4 amperes you want to set. So based on the 3 or 4 amperes, you need to have the amount of current in constant. Then you need to have amount of energy or power to be given to the system. Now, typically, if you look at the biggest shortcomings of electrical system or electrical propulsion system, is that actual power that needed. You need in terms of kilowatts. When I say kilowatts, that's already should be a mind-boggling. You know why? Because the whole satellite, sometimes very big satellite, even that whole satellite with all the systems that we have, maximum maybe we have 1 kilowatt, maybe 500 watt. It's good enough basically to last for another about 5 to 6 years. But not only one system, we have also the trusted systems inside. We have also electrical systems. We have all the other systems inside working. Total power budget that you need maybe 500 watt or even 1 kilowatt for the matter. But here, we need tens of kilowatts. Now, another problem is this. When the electric power or rather electric current, we set it maybe about 3 amperes. If you want to look into the actual power that you need, the only way to deliver that is to increase the voltage. That is the reason in these systems, if you look at the voltage, it can be at thousands of voltage. 1000 volt. Whereas if you look at in satellite, even if you look at a space station, the bus voltage is about 150, 160 volt. It's not much. That's a voltage with the bus. Satellite bus voltage 120 volt. That's a bus voltage. So based on that, so that is a big challenge in terms of doing this for a particular satellite application, especially for planet Earth. That is the reason if you want to go very far, we can afford to do that. But if you want to actually go around the planet Earth, the power budget, we can't actually meet the power budget. That means this power is very, very high you need. As I've mentioned, if you need a minimum of 1 kilowatt, let's say you need about a kilowatt, let's say, all these systems are the worst case, or rather the best case, about 1 kilowatt. With that power, you need probably about 500 to 800 at least volt, where your bus in satellite bus is only about 120 volt. So the big challenge here basically is their power. They are so hungry for power. Remember, ionization doesn't just like that coming, and you have to have a constant power. Power supply is constantly needed. Remember, I told you, you don't ignite and you close. No, constantly you need the power to run the system. It is basically an electrical, just like electrical car. This is electrical engine. You need the electrical power. Well, if you drive a car, it's easy. You have no power, you go and plug. But if you're in space, you can't do that. So the challenges are always there. We will do an exercise on this. So based on the exercise, I hope actually you can appreciate the exact system. Two things. You must understand interplanetary missions. Ionic propulsion is very, very important. Earth-oriented mission, it is not so interesting because of its high power budget. These are the two important things. But when we put these two systems together, that means there's chemical systems and electrical systems, we can go for interplanetary mission. That means from planet Earth, we use the chemical system up to a certain stage. After that, we move on with our electrical system. That is possible. Thank you so much.